All right, so now we'll look at the other example on this page. And this is another example where we're going to have to combine more than one rule. Because look at what you have. To differentiate this function y, which is written as a product of 2x plus 1 to the 5 and x squared plus 1 to the 4, well, I just said it, right? It's a product. At its outermost layer, the first thing you see if you look from the outside in is you're going to see a product. Now each of those factors are compositions of functions. So for example, the first factor, 2x plus 1 to the 5, that's a composition of two functions. And at some point, we're going to have to differentiate that first factor, just like we're also going to have to differentiate the second factor at some point. When we go to do that, we're going to need to use the chain rule. So this is another example where we're going to use the chain rule and another rule as well, except this time you'll use the chain rule later on. You're not going to open up with the chain rule like we did in the previous example over here. Okay, well let's start with the product rule then, because that's, like I said, that's what it is. First and foremost, it is a product. So if we write the derivative of y with respect to x, or you can write y prime, whatever you like. First thing we're going to see is the product, so let's write out the product rule. So we're going to take the derivative of the first factor, which is 2x plus 1 raised to the power of 5. And then we're going to multiply that by the second factor, but without taking its derivative, right? X squared plus 1 to the power of 4. So then our next term, we're going to do the opposite. We're going to leave the 2x plus 1 to the 5 alone, and then we'll differentiate the second factor, the x squared plus 1 to the power of 4. So that x squared plus 1 to the power of 4 is going to be inside the square brackets with our prime symbol. So that is now the first step. We've fully written out the product rule, but haven't actually executed the part where we take the two smaller derivatives. And you'll see that's a pattern. That's how I do things, and I encourage you to do the same. So on our next step, we're going to work this derivative out, and then we'll work this derivative out. But this is where the chain rule is going to come in, right? Because for this one, 2x plus 1 to the 5, you've got an inside function there, right? And then for this derivative, we've got another inside function, the x squared plus 1. So that's what we'll have to pay attention to. So let's dive in. So the first derivative here, well, treat it like it's something to the power of 5. If it was just x to the power of 5, you'd say, well, the power rule says that the derivative is going to be 5x to the 4. So let's write 5 times 2x plus 1, our inside function, to the power of 4. But then we have to multiply by the derivative of the inside function, which is 2x plus 1. So we've got to multiply by the derivative of 2x plus 1. Okay, so this now is the chain rule applied to this derivative, but we still haven't captured this factor, so we have to multiply that one in after. So x squared plus 1 all to the power of 4. So that is now the first term, right? There's still a little bit of differentiation left to do, but this is what the first term is going to be. In other words, that's what this first term turns into. So now we have this other term. So we're still going to have plus 2x plus 1 raised to the power of 5, and then now we're going to use the chain rule to take this derivative. So it's some function to the power of 4. That's how you should see it first. So if it were just x to the 4, the power rule would say that the derivative is 4x cubed. So we're going to multiply this by 4 times x squared plus 1, because that's our inside function, cubed. And then, of course, we need to multiply that by the derivative of the inside function. So you want to multiply that by the derivative of x squared plus 1. And that is now the chain rule. Both of the chain rule applications have happened, right? But there's still a little bit left to do. But this is getting down to the point where there's not much left, right? 2x plus 1, those are getting to be familiar functions now. You can handle those just with the power rule. You don't need any fancy rules. So this guy is just going to be equal to 2, right? Derivative of 2x with respect to x is 2, derivative of 1 is 0. So you got 2 plus 0, which is 2. Over here, x squared plus 1, that's the only other derivative. This is just a power rule application. So you're going to get this is equal to 2x. And that's the last of the derivatives. So now we can put everything together and see what we get. And we're going to get 5. Well, actually, why don't we slow down a bit here, and we'll see if we can get a little bit more done in one step. So if this is going to turn into 2, why don't we pull that to the front and combine it with the 5 as a 10. So we'll get 10 times 2x plus 1 to the 4. Then we'll still, so that got pulled out in front, then we'll still have the x squared plus 1 to the power of 4. And then what about over here in the second term? Well, the 2x and that 4 times 2x is going to be 8x. So why don't we take those, combine them, and move them to the front, because that's typically how you would write something like this. So we can write this as 8x. Then we'll still have the 2x plus 1 to the 5. That'll be the next thing. And then what else will we have? We'll have the x squared plus 1 cubed. That hasn't been accounted for yet, so let's put that in. And then that's everything, right? Because the 2x and the 4, they were already accounted for with the 8x. So this is what you get now. So technically, that is the answer. But this is just asking to be factored. There's a lot of common factors in here. So it's worth seeing how much you can pull out, I think. I mean, if you wanted to stop here, there's nothing wrong with stopping here, but I'm going to take the opportunity to fully simplify this just because there's a lot that can be done. For starters, there's a common factor. Well, there's a few common factors, but let's start with 2x plus 1. 2x plus 1 is a common factor. It appears as a factor of the first term, this first big term. It appears 4 times as a factor. And then in the second big term, 2x plus 1 appears as a factor 5 times. So we can factor out 2x plus 1 to the power of 4. So that's what I'm going to do here. I'm going to pull out 2x plus 1 to the power of 4. And all of that is going to be, that's going to be multiplied by everything that's left now. So for the first term, if I pull out the 2x plus 1 to the 4, I'm going to be left with 10 times x squared plus 1 to the power of 4. And that's what I'll have left. Now for the second term, I actually have 2x plus 1 to the power of 5. So if I pull out 2x plus 1 to the power of 4, I'm going to have one factor of 2x plus 1 left. So what we're going to have left here is 8x, 2x plus 1, no exponent this time, and then x squared plus 1 all cubed. Now, there's still more. Now let's look at the fact that x squared plus 1 is a common factor. And here it appears 4 times as a factor, and on the second term it appears 3 times as a factor. So that means we can pull it out 3 times. And by that I mean you can pull out x squared plus 1 all raised to the power of 3. So let's see what that looks like. So x squared plus 1 to the power of 3, and all that's going to be multiplied by what's left. So for the first term, if we pulled out x squared plus 1 to the 3, and we had x squared plus 1 to the 4, we're going to be left with one factor remaining. We'll have x squared plus 1, just with no exponent, or at an exponent of 1 if you want. And then what will be left here? If we pull out x squared plus 1 cubed, that's going to be all of this. So all we'll have left is 8x times 2x plus 1. And then now, well, there's nothing left that's obvious, except, well, we could pull out a factor of 2. We could pull out a factor of 2. Okay, let's do that. So if I pull out a factor of 2, what will I have? I'll pull the 2 right out in front, because 10 is divisible by 2, and so is 8. So we can pull out that factor of 2 now. So I'll get 2x plus 1 to the 4. This stuff out in front won't change. X squared plus 1 cubed, and that'll be multiplied by, well, just cut both terms in half. So we'll have 5x squared plus 1 plus 4x 2x plus 1. And that's it for the immediate factors to pull out. But we could now distribute this 5 into the brackets, distribute the 4x into the brackets, combine all like terms, and see if maybe what's going to be inside there, because it'll be a quadratic. There's an x squared term. When we multiply the 4x into the brackets, there'll be another x squared term. It might be the case that we can combine this into a quadratic that ends up factoring. So it's worth a try. We've come this far. Let's just see what happens. So here we'll have 2 times 2x plus 1 to the 4x squared plus 1 cubed. All the stuff in front won't change, but inside, what are we going to have? We're going to have, well, let's see. Let's check on the x squared terms. 5 times x squared, that'll be, well, 5x squared, right? 5 times 1, that's a constant. So just look for terms that are going to have an x squared involved. So 5 times x squared, that's going to be one of them. 4x times 2x, that's going to give you 8x squared. So that's going to be another x squared term. So we've got 5x squared from over here and an 8x squared from over here. So that's going to give us 13x squared, right? 5 plus 8 is 13, so we've got 13x squared. Now what about x terms? Are there going to be any x terms? This one won't have any x terms because we've got 5x squared, and 5 times 1 is 5, so there's just an x squared term, which we already accounted for here, and a constant, which we can get later. Over here, 4x times 2x, we've already taken care of that. 4x times 1, that's going to be an x term. That'll be 4x. But that's the only x term that's going to appear when we expand that out, so we can add that one down here by itself. And then lastly, just check if there's any constant terms, right? And we did say there's going to be one here. 5 times 1, that's going to give you a constant term of 5, right? Over here, you won't have any constant terms because 4x is going to turn this into an x squared term, and when you multiply 4x over here, you're going to just get 4x. So there's no constant terms over here, so we just have the 5. So we have times 5. Okay, now that looks pretty good. The only way you could go a little bit further than this is if you could factor this even further. And well, let's see, what would you need in order to factor this trinomial or quadratic polynomial? You'd need two numbers that add to the middle coefficient of 4. So they'd have to add to 4 and multiply to the product of 13 and 5, which is 65. So you need two numbers that add to 4 and multiply to 65. And it turns out that there aren't any such numbers. You won't be able to find them. So this actually doesn't factor any further. So that's as far as you can go. Okay, so like I said, technically this is the derivative at this stage. But if you, as you'll see later on in the course, as we get further along, especially when we get to chapter 4, once you find the derivative, you have to actually do stuff with it afterwards. So you're not going to want to have a form like this. You're going to want to simplify it as much as you possibly can. So why not get in that habit now? That's my mentality. So that's my motivation for doing that extra bit of simplification. But this is now as far as we can go.